All right, let's get started with Lesson 6, Experimental Error, Part 2. Now, in our first part of this lesson, we learned that experimental error exists in all labs, and there's no way that we're going to get around that. But there are certain ways to reduce experimental error. So in this lesson, we're going to learn what are the sources of experimental error and what we can do to reduce the experimental error in our labs. So first of all, what are the sources of experimental error? Okay, so we're going to focus on the fact that in experimental sciences such as chemistry, the results of experiments are never completely reliable, as there's going to always be experimental errors and uncertainties involved. So it is therefore important to be able to assess the magnitude of these and their effects on the reliability of the final results. So what you're going to be having to do in your labs is become very comfortable in identifying, analyzing, and evaluating experimental error. A big part of your lab report is going to consist of being able to do exactly this: identify, analyze, and evaluate the sources of experimental error that's going to occur in your labs. And as we get more involved in laboratory work, we will help you through this at the beginning, but by the time we're done, you're on your own. All right? And this can be challenging to identify, analyze, and evaluate experimental error. All right, so the first type of experimental error is known as random error. Now, we can think of random error is going to arise mainly due to limitations in an instrument's precision. All right, this denotes then that when we read a measurement, the reading can always be above or below the true value. And that's just because, again, we're going to always estimate the last digit of any measurement. And so your estimation of that last digit might be a little bit above or a little bit below the actual true value of what that measurement is, due to the limitation in your instrument. All right, so what causes random errors? Well, we've already expressed the major one, and that's the limitations in the measuring instrument's precision, or the estimation of the last digit. But there are some other causes of random error that we have to address and think about, such as changes in the surroundings, such as temperature variations and air currents. Now, in our class, we are not going to concern ourselves much with random error addressing temperature and air current variations, all right? Later on in your chemistry careers, if you advance or move on, those will become factors that will be addressed, and you'll have to make modifications and calculation changes in your laboratory reports. But for our practical purposes, we're just going to focus on the limitations in the precision of our measuring instrument. All right. So how can we reduce random error then? Two major things. First of all, obviously, we can use a more precise instrument, one that we can record to more decimal points. The better instrument precision that we have, the less random error that's going to occur. Also, a biggie, which we've mentioned before in part 1, is that it's important to repeat the experiment a number of times. Typically, we like to do it 3 to 5 times, and then we take all of that experimental data and we're going to average the values, and we're going to use our average value result as a way of looking at the reduced random error. All right. All right, so the final look at this whole thing about random error then is that because it deals mainly with the instrument's precision, and we'll never ever ever have an instrument that is perfect, as we've mentioned with significant figures. It's just not going to happen. There's always going to be uncertainty and problems with the measuring instrument that we use. Therefore, random error can never be eliminated whatsoever. Never eliminate random error. All right? You're always going to have an estimated digit or an uncertain digit. And that's just the way it goes. All right? All right, now, how do we record random error? Well, we have two types of measuring devices. We have digital devices and we have analog devices. Digital devices are pretty straightforward and easy to record the random error from. However, analog devices are a little bit more challenging. So we're going to look at that and practice that a little bit. The bottom line is that if you have a digital instrument, usually the manufacturer of that equipment is going to actually tell you what the random error is, and it's going to be expressed as a plus or minus value. So you might have a balance and that's digital, and the manufacturer will tell us that the random error is going to be plus or minus 0.001 grams or something along that lines. And so if we have a digital piece of equipment that we're using to measure something, whether it's temperature, mass, volume, whatever it might be, we will then give you the random error based on the manufacturer design. All right, so that's pretty simple and straightforward. So that then also kind of applies to A here, is that the uncertainty of a digital scale or whatever is always the smallest scale division. And I'll kind of, basically the bottom line is, if you had, say, a balance that could read out to the 1000th position, then that would tell us that the random error is going to actually go out to that position, and it would just be therefore expressed as the smallest scale division. So your random error, say the balance read 2.642, so the balance can go out to that 1000th position, and therefore the random error is expressed as 0.001. All right, but most of the time you don't need to worry about that, because on the digital scale, the manufacturer will give you what it is, and so you just have to record that. Okay, the analog scale is much harder though, because you have to look at the fact that in an analog equipment, you're going to have to take the smallest hash mark, and then you're going to divide that in half. So the plus and minus uncertainty is really the plus or minus half of the smallest hash mark. We'll give you some examples of all of this in just a minute. All right, so let's say we have a digital balance here. If the manufacturer says that the uncertainty is, the uncertainty is plus or minus 0.001, then according to our balance, we would record our data to 0.015 grams. That would be the mass of whatever object that was sitting on this balance. And then you would indicate the random error as plus or minus 0.001, okay? Now I want to point out a few things. What this means then is, since this digit is in the 1000th place, it tells us that this is our uncertain digit, all right? And we know that from significant figures that this last digit here, the balance is estimating. It's estimating it as a 5, but it may not be. All right, and so according to the plus or minus, remember that random error can be above the true value or below the true value. So what this is just saying is our actual value could be just as well as being 0.016, so plus 0.01 up, or it could be 0.0001 down, so it could be 0.014 grams. And so we know that this is what we're going to agree on, and the balance agrees on it, but this column here is being estimated, and it's indicated by the random error that we have recorded here. All right, so what that tells us is that whenever we record random error as a plus or minus, the last digit in the random error, or the last placeholder, must equal the last placeholder in our actual measurement. So since this estimated digit is in the 1000th position, our random error is also in the 1000th position, and therefore we obey sig fig rules. Okay, so here's another example. Let's say that the random error for this manufacturer is plus or minus 0.01 grams. Okay, so these two objects here weigh 9.30. So again, the balance suggests that these are the true values, and 9.3 it agrees on, and the 0 here, which is significant because there is a decimal point there. That's a significant 0, but it tells us that that is the estimated 0. So our random error exists in that spot, which is the 100th position. So therefore we write the random error as plus or minus 0.01. So again, our random error value matches the estimated digit value placeholder in our answer. All right, so what this could really mean then is the balance, or these two objects, could really be 9.31 or 9.29. So it could be one less or one up, okay, from this value here, and that's what that's representing in the random error. Hopefully that makes sense to you. If not, please come and ask questions or whatever, and we'll do some practicing of this a lot in class and in the labs that we do. All right, so now let's get to the harder part, the analog, okay? So what I have is 3 devices here that measure volume. We have a beaker. Oops. Let me go back here. So we have a beaker. This is a graduated cylinder, and this is called a burette, okay? So each one of these devices are measuring some kind of liquid, but not all 3 of these measures the liquid with the same precision, okay? So let's look at which of these instruments have the better precision, and let's see if we can determine the random error that exists, and then decide in the end which of these 3 volume devices to measure volume is the best that you would want to use in the lab that would reduce the random error. So let's look at the beaker first. You'll notice with the beaker is that the meniscus level is above 20 but below 30. So you know that the volume has to be greater than 20 but less than 30. But it's closer to 30 than it is 20. So what I would say is definitely we know that the value of that liquid has to be 20 something. And I'm going to go ahead and estimate that as 28 milliliters. Okay? So that's what I'm kind of assuming is that last digit, or guessing that last digit to be 8. Okay? You might think it's 29 milliliters. All right? But we should at least agree on the 2. All right? And so this basically is going to have 2 significant figures in our final measurement. the question is, what is the plus and minus value? All right. Well, according to the fact that this is an analog instrument, what we have to do is take half of the smallest hash mark, okay? So these are the only hash marks there are, and it looks like they're going up by 20s. So what we have to, or by 10, sorry. So what we have to do is take half of 10, since we're going up by 10, 20, 30, okay? So half of 10 is what? 5. So that tells us that the random error is going to be plus or minus 5, all right? Now you'll notice that my placeholder for my random error is in the same place as my estimated digit, which is what it needs to be, okay? So what does this really tell us then, if it's plus or minus 5? Well, it means that my volume could be literally 28 plus 5, okay? Or it can be 28 minus 5. It could be the volume. So in reality, this beaker has a fairly large range of random error. So it could be all the way up to somewhere in 33 milliliters, or as small as 23 milliliters. That's a pretty large range of values. And so the precision, I mean, you can think of, going back to precision of data, these numbers are not very close together. And so the precision here is not very good. And so what it tells me that the beaker is a very poor choice of using to measure volume in, with such a large random error and a terrible precision, okay? Well, let's turn to the graduated cylinder and see if we can get any better here. All right, so with the graduated cylinder, if we look closely, the volume has to be greater than 28. Notice that it's going up here. We got 29 right there and 28 right here at the hash marks. All right, so I can definitely say that the volume is at least 28, but then I could estimate my next place. And since we're going up by ones, then I'm going to have to do a fraction amount, so I'm going to have to do a decimal for my estimation. So it will be 28, I'm going to say 28.1 milliliters, okay? Now, since we're going up by ones, so we're 27, 28, 29, all right? So that's the smallest hash mark is going up by ones. So what's half of 1 is 0.5. So it should be plus or minus 0.5 milliliters should be my random error. And notice that this is my uncertain digit, the 0.1, and then my random error is in 0.5, which is in the same placeholder as my 0.1, all right, which is in the 10th place. So as far as significant figures go, it matches up just nicely, okay? So what this is telling us then is my range has now become much smaller than the beaker, because my numbers can be really 0.5 above that, so it could be 28.6 milliliters, or it can be 5 below that number, which would be 27.6 milliliters, okay? So what this has done compared to the beaker is that the precision is becoming better. The grouping of numbers are much closer in agreement to each other than what we found with the beaker. So the graduated cylinder is a much better device of measuring liquid in than the beaker. All right, now let's go ahead and look at the burette. All All right, we'll go a little bit faster now. So we got 29 up here and 28 down here. All right, so it looks like it's dividing even smaller increments. These are smaller increments. So we know again that our volume is at least 28 milliliters, but we can divide it down to a smaller number of, and these are 0.1. So this is going to be 0.1, that's 0.2, and that's 0.3, and that's 0.4. So I know that it's at least 0.3, and then my last digit I can estimate, okay, a little bit. So this estimated digit after 0.3, I think is going to be 1 milliliter. So you'll notice that my number of decimal points that I've been recording is getting larger, which means that my precision is getting better. And so automatically it tells me that if I look at these three measuring devices, the beaker by far is the worst because it's giving me the least precise volume measurement. And the burette is giving me the better size measurement. All right, so what is the random error? Should be plus or minus the smallest hash mark. Well, if the smallest hash mark is going up by 0.1, that's 0.2, and that's 0.3, and that's 0.4, it's just going up by 0.1, then half of 0.1 should be 0.05 milliliters. So my random error should exist in the 100th column, and it does match where my last estimated digit of significant figures goes. Okay, and so that's how we record random error and determining random error in your instrument device with an analog piece of equipment. Okay, again, we'll practice this more in class. All right, so let's move on. Let's finish up this with talking about the last source of error, which is systematic error. And we're not going to spend a lot of time on this video with systematic error because it's going to take a lot of practice to decipher systematic error. But it's simply systematic error is what's going to affect the accuracy of your experiment, okay, more or less. So what causes systematic error? The two big causes that we need to be concerned with is poor experimental design or procedure. If you design an experiment that is not very good, it doesn't collect very good data because of the way your experiment is set up, then of course you're going to get data that is well far away from the true or accepted value. All right, so poor experimental design is going to affect the accuracy or the systematic error, or create systematic error. Also, if the instruments that you're measuring have defects, in other words, they're not working properly, maybe your balance is broken, all right, that's going to obviously give you wrong data, and therefore it's going to create accuracy problems or systematic error. So how do we reduce systematic error? One is by, of course, then carefully designing your experiment and setting it up properly. Make sure that you're using good instruments that are working correctly, and make sure that all those instruments have been calibrated correctly. All right. Here are some different ways where systematic error can arise. If you're measuring the volume of water from the top of the meniscus rather than the bottom, would lead to values that are too high. Overshooting the volume liquid delivered in a titration leads to values which are too high, and so forth. These things that are listed here will get into more specifics as time goes on. So I'm not going to really address this in detail right now. All right. So finally, how do we record systematic error then? All right. We know how to record random error, but what about how do we report systematic error? In other words, how do we determine how accurate our experimental data is from the true value? Well, to do this, we are going to use what is known as percent error. And you're going to learn to calculate percent error and practice this throughout the year as you do labs. The bottom line is, this is the equation that you're going to use for determining the accuracy or the systematic error. So I want you to have this memorized and learn this equation really well. So percent error, what we do is we take the experimental data value, the value that you got from your lab, and typically this is going to be the average. All right, so we're looking at the average value that you take from all the trials that you have, okay? And then you're going to subtract that average experimental value to the accepted value, the value that I'll give you in class that we will say is the true value. And then you're going to divide that by the accepted and true value, and you multiply that by 100, and that will get your error into a percentage, okay? Now, if your error comes out to be 0%, what that tells you is that you're completely 100% accurate and there was no systematic error. So the goal is to get 0% error. If you can get 0% error on a lab, then your systematic error is extremely low and your experimental design is really good and your technique is really good, okay? However, if you ended up with, say, a 50% error, that is pretty huge, and that means that you're doing something wrong. Your experimental design is way off, and it's not very good at getting the correct or close to the correct value, and you have lots and lots of systematic error. And so you're going to have to evaluate where the error is coming from to create such a high percentage. In practicality, mostly we are going to shoot for in this class to about 5% experimental error, okay, or percent error. So if you find from your lab reports, once you do all your calculations using this equation, that your accuracy is about 5% of the true value or the accepted value, then you're doing really good. All right. All right, so the last, just note that experimental value may be an arithmetic average, which we just talked about, of a set of experimental data, or a single value. Mostly it's going to be an average from experimental data, okay? And then the sign can either be positive or negative, and that sign can tell us a lot about the systematic error that's occurring in your lab, okay? So essentially, this is all I want to address about systematic and random error for right now. This is probably very new to many of you that are first time in chemistry, or some of you have had chemistry classes in other places to really focus on this, but it's really important that you understand the difference between systematic error and random error, how to evaluate it, how to reduce it, and analyze it, all right? So, and to record it in your laboratory notebook. And so hopefully this is a start for you, all right? So that's all for now. Prepare for the quiz over this, and come to class with any questions that you might have.